corresponds to the very first part of abnormal EKG. This will be covered in class itself, but for those who want to listen to this prior to lecture or in addition to after lecture, you can feel free to do so. This abnormal ECG is divided into 3 lectures, 3 webinars. The very first part will cover some topics that include mean electrical axis and things that can cause abnormal voltage on an EKG. The second topic will be specific examples of abnormal EKGs, such as hypertrophy in bundle branch blocks. And the very last part is myocardial ischemia, injury, and infarctions, yet other things that can cause an abnormal EKG. Now, what I want to discuss first is the concept of a lead of axis and how we're going to utilize that to calculate what we call a mean electrical axis, which would be a means of determining the average direction of current flow through an individual's heart. If we look at Einthoven's triangle, Einthoven's triangle is considered to be an equilateral triangle, and each of these represents one of the leads, or the standard limb leads. You have standard limb lead 1 up here, standard limb lead 2 is over here, and standard limb lead 3 is right here. When you determine direction of the electrical current going from the negative to the positive recording electrode, we refer to that as being an axis. The axis of a given lead, such as here, this standard limb lead 1, this is considered the lead of axis. So what's the direction of the electrical current when we refer to this standard limb lead 1? What is it for standard limb lead 2? What is it for standard limb lead 3? What they do, what I can show you, I can tell you what the direction is. If you take these 3 limb leads, you break them apart, this equilateral triangle, break them apart, you collapse them and superimpose them over the heart. What you're going to get is something that looks like this. So you'll notice with standard limb lead 1, which is right here, I moved it down towards the heart, which you see here. What you'll notice is the positive recording electrode for standard limb lead 1, which is placed on your left wrist, is considered to be 0 degrees relative to the heart. If you look at standard limb lead 2, which is right here, that's moved up in this direction, you're seeing it right here labeled. The positive recording electrode for lead 2 is running 60 degrees relative to the heart. So that's our lead of axis. And lead 3, which you see right over here, was moved up in this direction. The positive end, or the positive recording electrode for lead 3, which happens to be placed on your left ankle, this is running 120 degrees relative to the heart. So before I go on, though, I want to review with you again where these positive and negative recording electrodes are placed on the subject. The positive recording electrode for lead 1 is on your left wrist. The negative is on your right wrist. The standard limb lead 2, the positive recording electrode is placed on your left leg. The negative recording electrode is placed on your right wrist. For standard limb lead 3, the negative recording electrode is placed on your left wrist, and the positive recording electrode is placed on the left leg. So what we have here, I'm kind of giving you direction of saying, okay, the axis of that particular given lead, but I'm going to use this. What you see here, I have actually created a circle, and what they've created is what we call an axial reference system. The axial reference system is going to be used to calculate the exact axis of the heart, and specifically the exact mean electrical axis of the heart, which will give you the idea of the average direction of current flow as it runs through the heart. What you see on this next slide is here is a circle, here was standard limb lead 1, here is 2, here is 3. But I've also included your augmented leads, because you can use the augmented leads too. And what you've created, if you use all of those limb leads, because augmented leads are limb leads too, they have what we call a hexaxial reference system. If you use just the standard limb leads, they call it a triaxial reference system. We will utilize this system in lab to be able to calculate that average direction of current flow. Well, what I want you to look at, when you look at this system, you notice we have a 360-degree circle. Starting at the left arm, this is your 0 degrees. That's where your positive recording electrode for standard limb lead 1 is. So that's 0 degrees relative to the heart. Starting going down, you run in 30-degree increments. And these are positive degrees. It goes all the way to 180 degrees. After that, it begins to measure in the negative range until you get back to 0. When we calculate a mean electrical axis, what we're calculating is the average of all the vectors, and specifically what we're going to be doing, the ventricular vectors. We're going to be looking at the QRS complex and figuring out what's the average of all those vectors, all that current flow that's running in the ventricles, but on average, how is it running? And remember, vectors use arrows. This here represents this average direction of current flow running through the ventricles. I see this big multicolored arrow or vector. The positive end of the vector is running or giving you an idea of direction. So you know this looks like it's somewhere between 30 and 60 degrees, how it's running. The size of the vector gives you magnitude. What we care about today is the direction. What is the average direction of current flow? So why should we even bother to measure this? Well, the average direction of current flow can change under certain pathologic conditions. So it's important to kind of have an idea if it's shifted. So different things can shift it. There's a correlation, though, between a mean electrical axis and also the anatomy of the heart. How the heart is situated in the chest wall, how the Purkinje system is arranged. But changes in the normal flow of current through the heart can shift that vector and give us some important bits of information. So the first thing to know is what's considered normal. Normal is if you calculate someone's mean electrical axis and this vector is running anywhere from 0 to 90 degrees, that is perfectly acceptable. This incorporates a lot of different anatomical variations out in the population. So things that may cause this to be more up here or down here, it's just how your heart is situated in your chest wall, how the Purkinje system or Purkinje fibers are arranged. Hypertrophy can be considered a normal factor that determines the axis, but I'm going to include that under things that can shift the mean electrical axis outside the normal range. But a little bit of hypertrophy, maybe if I started here, maybe shifted in one direction or the other. So the average, if they're taking like the entire population, you always say here's your Guyton numbers, the average is considered to be about 59 degrees. I'd say that's usually the average current flow is about 59 degrees. Now according to this, if I have my mean electrical axis is about 59 degrees, which standard limb lead would give me the biggest positive deflection for that QRS complex? Because this is what we're going to be using to determine the mean electrical axis. So I want you to remember one of the EKG rules. If a vector is running towards the positive recording electrode, it would be an upwards deflection. So this is telling you we're running towards a positive recording electrode. If it's running parallel or pretty close to parallel to the lead of axis, it'll give you your maximum deflection. So which of the standard limb leads, 1, 2, or 3, is going to give you the biggest deflection? Give you a little second. It's going to be 2. That's why we always show you what standard limb lead 2 looks like. It's always the prettiest, because that was always give you the nicest picture. Well, what can change or shift the mean electrical axis? I'm going to give you some examples. I'm going to start off with the example of what we constitute a left axis deviation. A left axis deviation is a mean electrical axis that is less than 0 degrees. Let's make a big point for you again. If I ask you, what is a left axis deviation? I'm pretty much asking you to define it for me. So you need to say a mean electrical axis less than 0 degrees. Do not say less than 0. You gotta give me units. It's gotta be degrees, and it's a mean electrical axis, which you can abbreviate as MEA. That's a perfectly appropriate abbreviation. Well, a left axis deviation means that the vector, it's running, here's where 0 would be. It's running up to the left. It's in that negative range. So, in mean electrical axis, I'm going to show you here, it'd be less than 0, and it actually goes up to minus 90 degrees. This would be going to someone to your left, a left axis deviation. There is some leeway they give to people if they determine your mean electrical axis, and it may be negative, it may be up to minus 30 degrees. That still is a left axis deviation, but it may be considered normal as long as there's no evidence of any pathology. The rest of your EKG looks okay, and any other tests they run are perfectly fine. But if you calculate someone's mean electrical axis and it's minus 20, don't say it's normal. It's still a left axis deviation. It's a left axis deviation due to blah, 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 blah. It may be a left axis deviation probably mainly just because of anatomical variation. That would be considered maybe normal. If you have a left axis deviation of minus 20 degrees and you got some other stuff going on, you got to tell me, left axis deviation as a result of blah, blah, blah. So what can cause a left axis deviation? 1, left ventricular hypertrophy. Number 2, left bundle branch block. Number 3, injury of the right ventricle. So we call it right ventricular injury. Those are 3 examples, and those will be examples we're specifically going to be covering in these lectures. So I want to show you over here in this picture a quick way of trying to figure out if someone has an axis deviation without having to do this fancy smancy way of calculating the mean electrical axis, of just looking at someone's EKG and go, wow, maybe it looks like they may have an axis deviation. So I call this the down and dirty way of determining if someone has an axis deviation. So if you look at someone's EKG, the standard limb leads, you should look at the QRS complexes, and the overall voltage of the QRS complexes in your standard limb leads should be a positive number. You shouldn't see a lot of negative voltage. And we can say the algebraic sum of the voltage. I'll give you an example of what they mean by algebraic sum. So if I want to know the algebraic sum of the voltage of this QRS complex, we'll say, hey, maybe this R is 0.1 millivolts. This S here we'll say is minus 0.5 millivolts. What's the algebraic sum of that QRS complex? So minus or plus 1 minus 0.5, or sorry, plus 0.1 minus 0.5, what are you going to get? You're going to get a negative number, minus 0.4. That's negative voltage. You normally shouldn't see that if someone has a normal mean electrical axis. So a big kind of flashing sign is you're walking along, and I do this in lab. I'll walk along, look at someone's EKG and go, whoa. In lab, when we run the standard limb leads 1 and 3, if I see a lot of negative voltage in lead 3, I'm going, oh, might be a left axis deviation. And how do I know that? Because me saying it over and over to myself, well, yeah, after a while I remember it. But here's a way to remember. I want you to kind of understand it. Is if you look over here, Einthoven's triangle. Here is standard limb lead 3. The negative recording electrode is placed on the left wrist. The positive recording electrode is placed on the left leg. Remember EKG rules again. If the vector is running towards the positive recording electrode, you're going to see an upwards deflection. If it's running towards the negative recording electrode, it's a downwards deflection. What do you see here? A big downwards deflection. So it's indicating to me that this vector is running towards the negative recording electrode. And where is the negative recording electrode for lead 3? It's at the left wrist, so it's running up here to the person's left. So I'm like, oh, a lot of negative voltage in lead 3. Vector's running towards the left. Left axis deviation. If this is backed up and you see a lot of negative voltage in lead 3, it's telling you it's significant. Because if you look at where the negative recording electrode for lead 2 is, it's way over here at the right wrist. So this is going up and up and over and over and over and over. It could be more up towards that minus 90 degree area. So it'll be a little bit more significant if you back it up in lead 2. A lot of negative voltage in lead 2 by itself, I cannot, if I just walk by and just see lead 2, I can't tell you if it's a left or right axis deviation. Reason? Let's look at the next one. Right axis deviation. You see here I've also drawn a lot of negative voltage in lead 2. So I'm just telling you that by itself can't tell you if it's right or left. You have to look at your standard limb leads. So let's define right axis deviation first. A right axis deviation is a mean electrical axis greater than 90 degrees. So here, I'm going to go back to this picture, earlier picture. It really is, technically, a mean electrical axis greater than 90 degrees up to 180 degrees. These ones up here, if it's minus or greater than minus 90, over in this area here, they consider it to be no man's land. They call it extreme right axis deviation. That is very, very rare, so I'm not even going to go there. But if it's okay with me, if you define a right axis deviation as a mean electrical axis greater than 90 degrees, you can define the left axis deviation as a mean electrical axis less than 0 degrees. That's perfectly fine for me for the abbreviation or for the definitions. Okay, so here, just as in left axis deviation, you have a little leeway. With a right axis deviation, if you have a mean electrical axis that's over 90 up to 105 degrees, that can be considered normal as long as everything else looks fine, even though it's still a right axis deviation. That person may be perfectly normal, nothing wrong with them, except they just have a right axis deviation. So it could be anatomical. What's the quick, down and dirty way of determining if someone has a right axis deviation? Look at your standard limb leads again. If you see a lot of negative voltage in lead 1, you're going to start to say to yourself, right axis deviation. So how can we explain it? Okay, so here we've got a vector running off to the right. So it's telling you that the vector is running towards the negative recording electrode. That's why you see a lot of downwards deflection. So in lead 1, the negative recording electrode is at your right wrist. So this vector is going up towards this direction. It's going to be past 90 degrees. So there's a quick way of just walking by, looking at your standard limb leads, and you see a little big honker S wave. You're saying, right axis deviation. If it's backed up in lead 2, it's going to be a little bit more to the right. Okay, but by itself, by the negative voltage in leads 2 can't tell you if it's right. You got to look at your leads 1 and leads 3. So what can cause a right axis deviation? Let's list them for you. Right ventricular hypertrophy, a right bundle branch block, and injury in the left ventricle. Those are 3 examples of things that can cause a right axis deviation. I want to give you a little tidbit of information, though, something that might be a little interesting. Remember I had mentioned to you that anatomical variations, or how your heart is situated in your chest wall, can affect that mean electrical axis. So here's something you may notice. It's not going to be absolutely set in stone, though. But people that are tall and lanky and thin, their heart's kind of, like if you look at the apex of the heart, it's going to fall more down near where the 90-degree mark is, instead of pushed off a little bit to the left, more, like at the 59 degrees or 60 degrees. So their mean electrical axis is going to be more towards, towards the 90 degree, and maybe a little bit to the right. Those are short, maybe a little chubby, little big bellies and stuff. That sometimes being overweight will move that heart up a little bit to the left. And so those people may have mean electrical axes a little bit more to the left. So it's a little bit tidbit of information that you may see. Now the last topic, before we go into the big guns and talk about the specific examples of abnormal EKGs, is abnormal voltage. So think in general. Muscle generates electrical activity. Muscle will influence the voltage that you pick up. So the more muscle you have, higher the voltage. The less muscle you have, the lower the voltage. That one pretty straightforward. So if you have more muscle mass, hypertrophy, great example, you're going to have what we call a high voltage EKG. If you've lost muscle mass, such as maybe having a myocardial infarction, where the muscle has died and been replaced with scar tissue. The scar tissue is not going to be generating depolarization, it's not conduct the electrical activity, so you will see a reduction in voltage with a loss in muscle mass. But people can lose, it depends on how much muscle mass you lose. It may not be as evident on an EKG unless someone lost enough muscle mass. Generally, as a rule, if you look at lead 2, if the voltage, overall voltage in lead 2 is less than 0.5 millivolts, that is considered to be a low voltage ECG. That would correspond to less than 5 millimeters in height. Okay? But another thing that can decrease voltage, though, would be anything that interferes with the conduction of the impulse from the heart out towards the chest wall where we have the electrodes placed. So if you have any kind of trapped air or fluid, that can interfere with the conduction through the chest wall. So things like emphysema, people get a lot of trapped air. If you've got pleural effusion, which just is a fancy way of saying edema in the pleural space, a lot of trapped fluid in the pericardium, those things can decrease conduction to the surface and result in an overall low voltage ECG. Good way to distinguish between a low voltage ECG as a result of things that decrease conduction to the surface or loss in muscle mass would be that if you have, say, a pleural effusion or emphysema, you're going to see low voltage throughout the leads. All the leads will be affected. If it's low voltage because of loss in muscle mass, that may be more localized, say, to your chest leads, because the chest leads are localized over specific areas of your ventricles, and maybe you only lost muscle in one of the ventricles. You can see maybe more localized to there instead of being overall voltage. So that's a kind of a good thing to kind of look for. I want to, though, is look at or discuss and give you kind of the relative parameters for what considered to be high voltage for when we talk about hypertrophy and muscle mass. There's a number of criteria out there what constitutes if you've got left ventricular hypertrophy or right ventricular hypertrophy. I'm just kind of giving you just a general idea right now. What would be constitute high voltage is if you have in lead 2, this is just a good way to look at it. In lead 2, the overall voltage of your QRS complex in lead 2 shouldn't be more than 2 to 2.5 millivolts. That would correspond, if you were just measuring it instead of millivolts, 20 to 25 millimeters. But if you look at your limb leads in general, leads 1 or leads 3, if you have R or S waves in your limb leads that are greater than 20 millimeters or 20 millivolts, that's considered to be more on the higher voltage side. Now the reason why I'm mentioning looking at leads 1 and leads 3 is because of Einthoven's law. Einthoven's law says, he stated, he happened to notice this, is that the sum of the voltage of leads 1 and 3 always equaled 2. So that's kind of something I just wanted to kind of tell you. If you look at 1 and 3, add them together, always is going to equal to 2. Okay, so that's kind of a good rule of thumb to remember. But if you see a lot of big voltage, and generally over 20, usually more 20, 25 millimeters, or that corresponds to 2 to 2.5 millivolts, that constitutes as being high voltage. You will see that with left ventricular hypertrophy. However, here's to throw the wrench in the works. Right ventricle never quite gets as big as the left ventricle. So it's going to be hard for you to see that voltage criteria I gave you for high, considered to be high voltage ECG. If you had someone's EKG prior to them getting hypertrophy and then see it after it, oh yeah, you're going to see the progression to higher voltage. But if you never had that before and after pictures, you just had the after pictures, you might not know that it was high voltage. But I'm going to tell you one of the ways that you will know that might be right ventricular hypertrophy is I want to show you, this is a normal 12-lead EKG. I just want you to look at your chest leads, V1 through V6. So in V1 through V6, this is perfectly normal to see what you see here. In V1, you'll start to see it's predominantly an S wave in V1 and 2. As you move to V6, you'll end up with predominant R wave. Now why does it look these different ways? Is remember the rules of EKG. Why waveforms look the way they do. If something is running towards a positive recording electrode, it's an upwards deflection. If something's moving towards the negative recording electrode, it is a downwards deflection. Remember where these chest leads are placed on the chest wall. So these, what you see here, constitutes what you would normally see on your chest leads. I also want you to notice here on your standard limb leads, you notice it's overall positive voltage that you see here in your standard limb leads. Now I want you to look at the chest leads in someone with right ventricular hypertrophy. Here, these are your chest leads with someone with right ventricular hypertrophy. What do you notice here? That's not an S wave, that's a big R wave. And so what you'll tend to notice with right ventricular hypertrophy is what they have is, instead of starting out with the S, they have an R. Independent, that one wasn't the perfect example. They have an R, and down here for V6s, they have an S wave. So it's kind of the opposite of what you expect to see in your chest leads. And it has to do because of how the current is flowing, or how the electrical forces are. Another thing I just wanted, while I'm here on this picture, is with left ventricular hypertrophy, I gave you kind of the criteria for your limb leads. And that's what I'm going to give you in case studies on your exams or even in assignments. But in your chest leads, the chest leads, voltage is always going to be usually higher in your chest leads because they're right smack dab right over the parts of the heart. If you have your S wave in V1, because that's what you normally see, is S wave in V1 or V2, if that's greater or equal to 30 millimeters, or I should say 3 millivolts, that's high voltage. R wave in V5 or V6, if that's greater or equal to 30 millimeters or 3 millivolts, that's considered high voltage. So the chest leads, they're always going to be higher voltage. One you just need to remember for me is kind of general idea for your standard limb leads. If you see standard limb leads, the voltage over 2.5 millivolts tend to be higher voltage. But you need some other stuff. What we're going to be talking about next, your next webinar that you need to look at is hypertrophy in bundle branch blocks, and we're going to elaborate a little bit more about hypertrophy, looking at some other things you need to be aware of if someone has hypertrophy.